which would be delivered to us is speaker and language recognition, leveraging deep neural networks and self-supervised learning. And the expert for today's talk is Dr. Mohammad Azharuddin Laskar. So, a brief introduction about Sir. Dr. Mohammad Azharuddin Laskar works as a senior data scientist at Armsoftech.AIR Private Limited, Chennai. His area of research and development work includes speech technology, natural language processing, large language model, and customer analytics. His primary research interest lies in machine learning and deep learning based speech modeling for various applications. He has served as a resource person in a number of FDPs and lecture talks on data science organized by NITs, IIITs, etc. He received his doctorate degree from the Department of Electronics and Communication Engineering, NIT Silchar, for his thesis titled Machine Learning Based Acoustic Model for Text Dependent Speaker Verification in the year 2020. He has published a good number of journal and conference papers on speaker verification, language identification, etc. He has also worked as a project engineer at NIT Silchar under a DET-sponsored Gulf of India project. He obtained his MTech degree in electronics design and technology from Tezpur University, Assam in 2014 and BTech in ECE from NERIST in 2010. Sir, I would like to welcome you and I would like to hand over the stage to you.
Right, right. Thank you so much. Thank you for the introduction, and I'm really pleased and honored, to be a part of this workshop. So thank you for inviting me. And I'd also like to mention, it was just around 2016-17, I myself attended a workshop in Sikkim Manipal Institute. It was conducted offline. So I must say, workshops like this, do help us, get a better perspective at times, and helps a long way down the line. So thank you, for having me. So today, I believe it is almost the second last day of the workshop, and since we are discussing speech technology, so I'm sure, there have been many talks already, and some professors, some experts from elsewhere, and definitely, as we go along with the topic today, we can see there will be some overlaps, because I mean we round about discussing the same kind of stuff, but maybe applications are a bit different. So but still, I believe, when you get a defined perspective, it helps. So I shall start my presentation. Let me share it, and maybe to save some data, I'll just put off my camera as well. Just let me know if my screen is visible, and am I ready to go?
Yes, it's perfectly fine.
Yeah, okay. So the topic is speaker and language recognition, leveraging deep neural networks and self supervised learning. So we having this talk today, because we're discussing speech technology opportunities and challenges, and all of us know it very well. We are mostly going to focus on artificial intelligence and the kind of networks that are helping us achieve the accuracies, and helping us bring it to practical fields and develop applications on top of that. So we know it is mostly going to be all about AI. At the same time, what are the intuition uh, behind this, how we actually went about engineering, and went on adopting AI for this kind of applications. This is what we'll try to develop, build up on a bit of a background, and then we can move ahead. So this is how I just spend my presentation today. After introduction, we'll just discuss the speaker and language recognition. Will cover all the three areas, like the traditional approaches, the deep learning techniques, and the self-supervised learning, which is more of a recent thing. And we'll discuss the real world application, the challenges that. So Yeah, I don't know what was it. Was it some network lag or something? Okay. Hello. Am I audible?
Yes, sir, you are audible.
Yes, sir. Yes, sir.
I disconnected for a while. I'm not. Yeah. Okay. So like since we've decided that we'll be looking into speech and like we want to develop application based on speech, so we have to see how we can engineer it, and to be able to engineer it, like we have to look at it with a particular perspective, like so we know it is all about a signal. So I mean, we don't know what to do with the signal, so we have to understand the phenomena behind it. So there are two aspects that we usually look at: the speech production and the speech perception. Okay, I mean, you have had like talks based on ASR and language modeling, everything. Like, no, it's very important, what perspective we are trying to look at, and wha- what is the intuition behind the different kind of featureization or different kind of models that we adopt. So these are the two basic aspects when it comes to speaker verification and language recognition, or speaker identification. So speech production and the speech perception are the two like aspects that we got to look at. Like, so what constitutes like speech production is like the neuromuscular commands that we say. Like, I mean, our body is like driven by muscles. Okay, so like even when we talk, like hundreds of muscles come into play that they talk about, and the way those muscles are signal is through our it comes from the brain, like with the help of all these neuron network, like so that's what they are talking about. Then movement of speech production organs, whenever any speech sound comes out, obviously the are going to move. We have this acoustic pressure variations, which is actually the speech signal that we talk about. We'll see how we have to digitize it, and to be able to bring it into computer and do all the processing that we're doing right now. And we just don't make any sound. We have some kind of language coding. We mean something meaningful out of it. Okay, so we have some understanding and some knowledge and some training, which is why we know how to formulate the message. Okay, so this is roughly what speech production involves. So when you the speech perception is related but a bit different in the sense, like what the person is hearing, how the person is hearing it. Okay, when a person listens to you, how does it feel for him? So it's that person has to hear it with his ears, like that the whole organs are involved, their auditory processing, then the intelligence and everything gets involved there. So we have this cognitive integration, and one has to have the idea of one who is trained and matured and knows how to understand languages. They will know like how to segment speech and how to detect the word boundary. So I mean, people don't put in any effort explicitly, but it is more or less it comes with training and as we grow up. So you see, this is the basic framework, so to say, like depicting the two aspects. One is the human speech production, and the other is like uh, here is we mainly like discuss the speech production actually. So we have the motor control, as I just mentioned. There are a few organs. I mean, I'll just like quickly go through, like velum, tongue, lips, and jaw. So we know exactly what are these. I mean, when you had a talk on ASR. So there was a very detailed elaboration on it. So I can just go quickly with it. Then we have this glottal source and vocal tract and speech. So here is something that we have to understand. Like when, when we discuss ASR, we are so concerned about the phonemes. Okay, what exactly a person saying. But when we talk about speaker verification, like we'll have to see like what is more important for us, because there's something called the we have the vocal cord, we have the vocal tract. Okay, we have all the articulatory organs. So these are most differ from person to person. Okay, and that could be the basis of how we go about like detecting speaker. Okay, that should be our intuition, and we will lay our foundation on this fact itself, like that uh, different people will have different speakers. For say different speakers will have a different physiological not structure in the sense, like I mean, fundamentally they are same, that there will be changes in the size, shape, tenacity, and all those stuff. So those, if you could featureize well, we'll be like good to go ahead and like classify speakers. Similarly, like when it comes to language identification, we have to see what are the things that we have to target. Okay, I mean in language identification, I mean vocal track changes, it's not something which is going to help us. Okay, if a person is very tall, if a person is like a little dwarf, I mean, so there could be some difference in the vocal track. A grown up person and a kid will have a different length of vocal track. So that is not going to affect our language, but it does affect how we perceive speakers. Okay, so we have to see what are the areas, what are the phenomena that we can target when we want to do speaker recognition, and the phenomena we can target when we do language recognition. So this is how we lay the foundation, and we build up an intuition and go about developing systems. So I mean, as we see, so the speech, it has all these aspects, and there are different things that we can do out of it. Some of the major areas and applications, I've just listed it out here. We have speech recognition, speaker recognition, language identification, emotion recognition. So we will stick to speaker recognition and language identification in this case. So obviously, when we talk about speech recognition, is about understanding the meaningful words and in their context. Okay, similarly, emotion recognition is obvious. So we are not doing that. We want to understand what language the person is speaking and who exactly the person is. So building on that phenomena that we talked about, we can narrow it down further and see exactly uh, the physical aspect of it, what exactly are the cues that can help us do language recognition. So we have acoustic phonetics. Okay, this mainly, all the languages have different phonemes. Okay, we our languages, we have every language has a set of phonemes. Okay, some have more, some have less. Okay, which is why they call there's one having there's a big range when we have a lot of phonemes. Okay, mostly it is to be in 40 house 40s. So Indian languages basically the number of phonemes in the languages are mostly in the 40s. So okay, this phonemes are very language specific, but many times different languages share the phonemes. Okay, so they cannot be a sole basis of our discrimination or classification. So phonotactics is another area where, this studies how two phones come in together. Okay, because there are rules in languages where, you cannot, there's sometimes there will be two phones which cannot be spelled out together. Okay, it will sound very awkward, it would mean nothing. Okay, first, and that thing differs from language to language. Okay, so this is another area that you see, when we do this, the first point was about phonemes. Okay, so if we can recognize the phonemes specific to a language, we done the job. We recognize which language the phoneme is coming from, the utterance is coming from. Second, when you phonotactics, if you know there's certain combination which occurs in a particular language, and if you are able to detect it, okay, so that our job is done. Similarly, we have prosody, which might differ from language to language. Prosody usually involves pitch and energy and duration. Okay, so next we also, of course, synthetic, lexical, and vocabulary. Every language has these aspects. Okay, they have their own vocabulary, they can have their own script. Okay, lexical, they have their own syntax. Okay, so certain languages have a very simple, I mean, the way we understand it, subject, predicate, object. Okay, but there are certain languages which do not have it that way. I mean, even among the Indian languages, this is not followed. I mean, this particular pattern is not the same across different languages. So that could also be a basis for us to identify which language the person is speaking. Similarly, when you talk about speaker specific cues, obviously vocal tract characteristics is something which is most important, because I mean, this is at physiological level we understand, this is different from speaker to speaker. Okay, so then we have voice quality, timbre. Every person, when it comes to singer, they have a bigger range. Okay, when they can produce a lot of harmonics when harmonics of the speech sound, because of the training they have. Okay, so that could also be a basis of how we can recognize people. And we have articulatory features. No, it involves jaw, teeth, tongue, and everything. The mouth. Some have smaller mouth, some have bigger mouth, some have that would result in bigger cavity or smaller cavity accordingly, and that will definitely bring about characteristic changes in the sounds that come out. So that could be the basis for us to target and exploit and see how we can featureize it, and that can help us produce the voice print that we're looking for. And speech dynamics, like person to person, the speech dynamics differ in terms of how they speak, how fast they speak, okay, how slowly they speak, or do they do any kind of modulation, or they just speak like plain, okay. So those factors can also come in and help us detect speaker in a better way. So when it come to India, challenges are there, this so far, we have identified the phenomena, okay, how this speech comes out, and we understand how we can target certain characteristics, certain features, whether we want to do speaker recognition or we want to do language identification. But it's not that straightforward, because there are challenges in it, okay. Because as you can see, Indian languages itself can be of different category, and so on. And in each of these categories, the languages would share some they will have some commonalities, and they will have some differences, okay. So these commonalities cannot be the basis of our discrimination, okay. So that's why the study of these categories is so important, okay. When you can Indo-Aryan, Dravidian, like Native Burman, Austrosistic. I stay right now I'm working in Chennai, so most of the time I was in northeast. So I can when I was in northeast, as I went across like North India, even though I didn't understand the language, I could make out, I mean, someone is speaking. But when I initially came down south, it took me a while, like, before even understanding whether this person is actually saying something or just blabbering, because I was not aware of the phonemes. So such differences do exist. So I mean, that is why it is important to categorize languages and then study each individually, and then across different categories we can find the commonalities and normalize it. If you really want to do like language identification, of course, if we want to first do a hierarchical system, that is also a very popular way of doing things these days. Like, we can create a hierarchy where you can initially categorize the language in a particular group, and then within a group it becomes much easier to uh, further classify the languages. Similarly, there are types of languages, like tonal languages, non-tonal languages, okay. Simply based on the tone, like, certain words would mean different things, okay. I know of Manipuri language. I heard of Manipuri language, which is like when we're doing our work, our research. So there's very tonal, like, I mean, the same word could mean different things based on how we speak it, I mean, the tone that we speak it. So like, I mean, besides this, like, there are other factors, like, this is the inherent challenges that we have. The other challenges, because comes in, by virtue of the way we communicate things, and the virtue of the way the speech comes to us, or we capture the speech. So there are variabilities in environment, okay. Those once it comes out of our mouth, or it goes to a communication channel, when we talk about phone or video call, so it is exposed to a lot of disturbances, okay. So those variabilities will also, we ingrain in the signal, and that makes life difficult for us, okay. So when you talk about, like, languages, different speaker will still have some different speakers, even though of the same language, even though they have the same mother tongue and speak the same language, they will still have some variability, okay. So it's important to normalize the speaker variabilities out there. So that is one challenge. Of course, channel characteristics, okay, and different, when we do like communication over VoIP, or when you do over telephonic line, okay, or mobile towers. So it has got its own characteristics, disturbances, which gets ingrained, and it's important that we normalize it or do something about it, so that, like, our accuracy doesn't come down, okay. And languages, I mean, especially like in India, we have languages. Each languages could have many dialects, okay. So I mean, so again, like, it's important to look into the different dialects. You cannot just generalize, okay. If a certain language has 4 or 5 dialects, you cannot be training your model with just one dialect of it and claim that that language is a part of the system, okay. So we have to get all the dialects involved, and of course dialect identification itself is another area of work. So and similarly, like, like similarly, like we have challenges in speaker recognition. Okay, like uh, here the challenges of it are of a different nature, because the application is in fact of a different nature. So you see a people's voice, okay, keeps on changing. Okay, even during a particular day also, the voice may not be like the same, like someone after the voice that we have, like right after having food, and just before having food, or right after having like like a run or or a sprint of exercise. Okay, so our voice would differ, because the way like the bodily factors will come in. If you are tired, if you are hungry, if you are not in a good mood, the voice do differ. Okay, I mean, for normal person, like for day to day, like we can actually recognize our peers or our family members, even though they could be in a different state of health, different state of stress or emotion. Okay, so but like when we put everything in terms of signal, okay, and we make templates, so those variations bring about a bring about a lot of changes. Okay, and that actually makes life difficult for us. Okay, so until and unless we address these issues, okay, so we are bound to make mistakes. Okay, so age and the health of the person and the stress and the emotional state, okay, so those things come into play. We'll have to figure out a way to normalize these things. Okay, so that even if these factors come in, our the feature that the embedding that we created, the template that we created for the speaker doesn't have much changes. So only then, like we can have our system intact, or there will be like issues. So exactly, like, and then obviously environmental noise, it is always been a hurdle. Okay, because of background noise or crowds or traffic, it's not very easy to like filter those things out. Okay, so whenever you try to filter something at a signal level, like you always run the risk of disturbing the characteristics that you are actually looking to, like capitalize on. Many times, like we look for specific characteristics, but like because of you want to remove the background noise, sometimes you want to remove the traffic noise, but you do some signal processing, put some filter on it, or use some neural network to do the filtering or speech enhancement. But what happens is, like, you actually lose out on the information that we were banking on, and to be able to classify speaker. And that's why things are a bit complicated. Like, so similarly, like communication channel also, like puts in its noise and disturbances and all the artifacts into it, and things become challenging. So to talk about, so this is so these are the issues, and like these are the aspects that we discuss, and now how we approach it, like the engineering that comes in. So I mean, I'm sure this is very obvious. Okay, I'm sure, like all of us here today, like, are aware of it, but still I'll run through it. Like, the classical approach usually includes this pipeline, you see. uh, but, yeah, I just, for a moment, I thought I got disconnected. Okay, I mean, if I just disconnected, like, I just hope, like, someone can pick me over WhatsApp. Yeah. Okay, so we have the classical approaches, where we do the hand coding of features, and then we use some machine learning algorithms or create template without any machine learning as well. And then we do the scoring and classification. Okay, and other issues also needs to be handled, like channel normalization, noise cancellation, score normalization. Okay, and we have to encounter like a normalized condition variability, etc. All those stuffs will come in. So, like, you'll find my presentation a bit like heavy towards like speaker verification, because that was something I've been working on for a long time. So you see, this is the basic framework we used to use for doing text dependent speaker verification, the most basic. Okay, and though it may be very basics, and in the world, like, since I've been like, working in the industry for 5-6 years, I can tell you, like, many times we still resort to this technique. Okay, given the bandwidth we have, the computer resource, the bandwidth, the response time that is like, in demand. Okay, many times we cannot move on like towards like very heavy models, like, the state of the art model. So there are systems where we still use this kind of technique, where it works very well. So mm, when we do speaker recognition, how we do it, like, we have this enrollment session, and then we have this authentication session. During enrollment session, like we capture the speech from an individual. That's a part of training. Okay, not training exactly. We the model has to be trained. Like either you can train a model like using a lot of data, or you may just start like just use the utterance that is given by a speaker as part of this enrollment. Okay, so we have the enrollment speech. We do some pre-processing and then feature extraction. Okay, and then like maybe we store it in terms of some like template, and then when we do the authentication, we follow a similar pipeline where we do the pre-processing, feature extraction, and finally uh, we get the similar template and we do the scoring out of it. We set some threshold. If the similarity is really high, then probably it's the same speaker. If not, it is lesser. So this is the very basic system, but it is still very functional, and still we use it in a lot of systems. I mean, in the whole package of services that we have. Okay, so speech featureization, like it's basically a parametric representation of the speech signal. Okay, and when we do it for like speaker recognition, we have to ensure that like whatever we featureize, it has to like encode more of the speaker characteristics, and not of like emotion, or not of like a language or any other stuff. Okay, that's the target that we have. So but what has been observed at MFCC has been like good for a lot of applications. Okay, and this has been, it is still one of the most used like features that we have for speech applications. Okay, so here like we just do some frequency transformation. Okay, and then we have this log module, and when again we do discrete cosine transform to get those captures coefficients, and those captures coefficients happen to be happen to be very powerful in terms of capturing the spectral features. Okay, and that could represent the vocal tract quite effectively. Okay, so this is one feature, and like one of the very basic way of doing thing is like DTW MFC. DTW stands for like dynamic time warping. Okay, so given two vectors, like a little while ago we discussed like when we get some utterance from a speaker, we featureize it, and once we featureize it, we must store it as a template. Okay, so and at the time of authentication, we get a similar template, and now we have to score it and see whether it is from the same person or not. Okay, so here what happens, like we can use dynamic warping to do the scoring. Okay, why dynamic time warping? Because like you see like when the same person speaks, he would not speak it in the exact same way. Okay, during enrollment say like he spoke very fast, but during authentication he's speaking very slowly. Okay, so our system cannot make that as an excuse. Okay, it has to be able to like determine whether it is from the same person or not, whether he spoke is very fast or very slow. Okay, so this DW is very good at aligning these things, even if the two templates are not of the same length. Okay, if someone speaks slowly, you see the length assuming we speak the same thing, the length would be very larger compared to the utterance which has been spoken very fast. Okay, so there is a mismatch in length. So mismatch in length means mismatch in the number of samples. Okay, so how would you score then? We cannot score one to one. Okay, so DW is a very good way of doing it. Okay, so it aligns dynamic time warping. It aligns those two templates. Okay, and gives you a final score based on it, which you can take a decision. Okay, whether these two there's no fixed threshold as such, because that we decided based on our experimentation, and if we have sufficient sample size of speakers. Okay, we do the testing and we decide on a particular threshold to assure that we get the kind of ER or the accuracy that we desire. Okay, and prior to every in classical approaches, it was very important to do some kind of voice activity detection. Why? Because we don't want to featureize silent regions, because even between words we have silence, and when we put on a microphone, when we start speaking, usually like we take some time before we utter our first word. So there's some silence before the utterance and after the utterance. So it is always a good idea to actually remove those things before we go into processing it and featureizing it. Okay, that helps improve the accuracy. Otherwise, I mean, if the silences are if the silence regions are very consistent, maybe you would not see much differences. But if suddenly the silence regions are are like have a good proportion of the utterance, then definitely like our system is going to fail. Okay, because that those would interfere with our features, and that would interfere with this scoring. Okay, so this is how the whole system would look like. You have the pre-emphasis and voice activity detection, MFCC extraction. Okay, then this is capstone means subtraction. This is a standard way of doing it, because like since like we discussed, we have to account in for a lot of things like channel variability. Okay, so this is one of this method to do channel at capstone level. If you do the mean subtraction, a lot of noise which gets convolved with the speech signal, that can be actually separated. Okay, and that helps us like get better accuracy. So this is something we've already discussed. Then coming this is a little more more involved in terms of like machine learning. So we heard of this GMM. It's still the one of the most powerful model that we have, like Gaussian mixture models. Okay, the picture itself like is very obvious, right? I mean, this is a statistical model. Here we can build it on top of the features that we just discussed. We can continue with our example of MSCC. Okay, so since we have those features, we can build a Gaussian mixture model. This will it's a probabilistic model which it will like mimic a distribution for whatever features we have. Okay, given the features we have, it will mimic a distribution, and and it will tell us like this set of features fall in this kind of a distribution. This is the distribution of the features here. So if we can fix that distribution, we know how a person a speaker voice looks like. I mean, in terms of probability distribution. Okay, so that could actually act for us as a template. And this distribution is nothing but a set of means and variances when we talk about Gaussian mixture model. Okay, so I mean, there are some examples that I've cited here. You see, like 100 minimum for 60 seconds may be required for a high security application. Okay, so this what is 60 seconds? It's like the length of the utterance that we have. Okay, so in every system, as we know, when we do speaker recognition, the first step is obviously acquiring the enrollment speech. Okay, and there's a debate as to how long can be the enrollment speech. So if a very like high fidelity system, like I mean a small short utterance would be enough. Okay, but for a less for a less heavy model, okay, you might require a longer utterances, so it's able to capture more information from the speaker, and then and do the classification later on, or the verification in that sense. Okay, but I can tell you like I mean in these days, like even 5 to 10 60 seconds is obviously too much. Okay, I mean, even people talk in terms of like 2 to 3 seconds. That's the kind of, especially like the industry that I'm working in. Okay, so the application that I work in, it demands things to be done in a matter of 2 3 seconds. Okay, so that's the time that we get. 3 seconds is right now what it's working right now, like the system that we have built at our company. So it just requires a 3 seconds kind of data, and it's able to recognize speakers. So like this is all about GMM. So like I mean, if since we're discussing the hierarchy of things, you see, like we started with features and we saw DTW, and we went a little ahead and so GMM can be very powerful. Okay, now this eigen voice. Okay, eigen voice, like it is similar to principal component analysis. Okay, so if you have if you have a data manifold, okay, so it is always easy for us to find out the different directions which are more important for a particular application. Okay, so given, because these are multidimensional data vectors that we're talking about. Okay, so it will it will it will make a that will represent a data manifold, and and all those directions in the data, all the axes are not as important. Okay, and so it is important, we can find out some uh, like the most important directions. So it is not exactly PCA, because we do a lot of we do actually factor analysis here. Okay, I mean, given the direction, we want to find the best hidden directions. Okay, hidden accesses which are more important, like when it comes to certain applications. So in this case, it can be speaker recognition, or it can be language recognition. Okay, so here, like when we talk, it is built on top of GMM again. Okay, GMM, you see, like suppose GMM has got like the 32 mixtures, you see. So like like it will have 32 means. Okay, so that will form a super vector. Okay, that kind of a main super vector. So like we can work on that, then we can do some dimensionality reduction. Okay, and then do this use this vector analysis techniques and eigen decomposition, and come out with an eigen space. Okay, and that in that eigen space, all the speakers would be represented. And once we develop an like good enough eigen space, like after training it with data which represents the universe. Okay, which is, you see, I mean, we don't have to take into consideration all the people in the world, but like it has to be representative enough. Okay, we have to take a good sample of data, and then when we do when we try to project a new utterance. Okay, first we featureize it, do the GMM, get the means, and then again project it on this space. We'll get that exactly. Here you see in this example 20-dimensional vector which will represent that speaker. Okay, and it will be very efficient at differentiating one speaker from another. Okay, there are techniques how we do it, like maximum likelihood, like the detection, and then with maximum likelihood with distance detection as well. Okay, so this is one technique that we use. Okay, so these are similar techniques that we discussed, like joint factor analysis. Again a part, it's again a factor analysis technique. Okay, finding the right directions. But here what they do, they want to say that, like when in the speech signal we have the channel information as well as the speaker information. Why not separate it? Okay, so here they try to separate it. Okay, so it separated it, and so that way, your like eigen voice matrix, which is represented by V here. So it should be more capable of like representing the speaker space. Okay, and hence once the speaker space is ready, once we project a new utterance into it, we get the exact template for that particular speaker. Okay, so joint factor analysis was a I mean was state of the art at certain point of time. Okay, so that led us to iVector. In iVector, what they did, like just in a way, they came back and they said, like, we should jointly, I mean, create a space for, like, channel information as well as speaker information. Okay, so this works well, like when we much larger amount of data. If you have much larger amount of data, and then we don't care about separating the two things. We take the two things together, and that's why this T actually stands for total variability matrix. It has got both the speaker information as well as channel information. Okay, and and this iVector is still one of the most used systems, you see. I mean, be it language recognition or be it speaker recognition. Okay, even the state of the art, like ASR system, if they want to use some of the speaker embeddings, it is iVector itself. Okay, so iVector is one of those breakthrough techniques, like which has quite revolutionized this technique. Until recently, many of the systems that we work on, were iVector based. Okay, so you see, like we had as you can see, like I actually did not put in a lot of numbers because those numbers are very obvious and easily available. Okay, I just wanted to share more of the perspective that we look at while building systems and choosing models. Okay, so so these are the like this IVT is one of the system, and it has to be followed by some of the other like ancillary techniques like LDA, WCCN, so that we can handle those variations that we talked about. Okay, so this how is once we have the I vector is like embedding. You see, like in the it's again built up on GMM, just like joint factor analysis or Iron voice. So it is again built on GMM. We take the means and make a super vector out of it. Okay, and we build a space, I vector space, the total variability matrix, and then we each of those things represent an I vector. Okay, if any projection on that space represents one I vector. So this like we got to do some kind of like within covariance normalizations, preclination normalization sometimes. Okay, and PLDA is like it's a kind of scoring, like because instead of just scoring cosine scoring, okay, we can do like probabilistic linear discriminant analysis. Probabilistic linear discriminant analysis, like it helps in two things. Like if we have data like channel wise. Suppose microphone, you can have the same speaker speaking through microphone or some other devices, okay, input devices. So if we have such utterances channel wise, you can train one PLDA, like probabilistic linear discriminant analysis. So it helps in discriminating. So those channels variation would not affect and come into play. Okay, it will kind of normalize it, and then we can score. It's again based on some similarity. Okay, it will score. It will see if that particular speaker falls into that particular distribution. Okay, whether it suits the universal distribution more, or that particular distribution more. Okay, distribution of features that we have, the probabilistic model that we built. Okay, so that PLDA helps in doing that. PLDA still, even in the state of the art models these days, like once we get them, suppose we're not doing iVector, but we are using some deep neural networks and get the embeddings. Funnily, like in many of the systems, they still use PLDA as the backend model. Okay. Now, of course, these things have to go along, like feature normalization, okay, channel compensation, and session validity compensation. So you see, like this how classical approaches basically, had these things in, like we have to certain stages, like we have to do the featureization, and then we have to do the modeling. We had to do a lot of corrections in terms of feature normalization, channel compensation, sensation variability, and all those sort of things. Okay, so with the advent of this deep learning techniques, when more data kept on coming, so things got a bit easier, in the sense, like we had lesser number of steps, but it's not easy to train such systems. Okay, we need a numerous amount of data. So initially, for language recognition and speaker recognition, we talked about D vector. From I vector, we then started talking about D vector, where this D vector were basically like embeddings from one of the layers of the deep neural networks. Okay, now there were research, I just noted it for reference. So uh, different DNNs could be trained, one uh, d- you could train a DNN to classify speakers, you could train a DNN to classify phonemes. Okay, or you could jointly train a DNN to classify both phonemes and speakers. Suppose same phoneme spoken by different speakers would make different classes. Okay, so you have those sort of training samples. So like when people started, they started with testing with different kind of deep neural networks, and all of these had their own cons. Okay, so you see the results are tabulated. You can see like mostly these are the numbers in terms of, you see, ER. Okay, equal error rate. That's the metric we use for like both speaker recognition and language identification. Okay, so uh, in terms of language identification, of course, we have to ensure, like we're talking about PS, okay, when we talk about ER. So you see, here we also talk about tandem features. Okay, so one technique was, we'll use a D vector. Okay, once we train such model, okay, and then we can use any of the activations from any of the layers, and then we can combine those with already existing layers, already existing features that we know about. Okay, like MFCC, PLP, GFCC. A lot of features like gamma tone like frequency capture coefficient. So those features have been known to be performing very well. So we can use D features, and combine it with already hand coded features that we already know about, and that would make the tandem. That is known as a tandem feature. Okay, and then we can build a classifier based on it. Okay, and we can again go back to GMM UBM, or we can again go back to like GMM UBM, or it can be like DTW dynamic time warping, or we can still go on top of this itself, on top of this D vector itself, we can train another I vector system. Okay, and people have done it and found good results out of it. So this is how we started looking at speaker recognition. Now came this TDN, and from D vector, from I vector we graduated to like D vector, and we next switched to X vector. X vector is still one of the de facto like standard today. So you see, in language recognition or speaker recognition, what is the intuition, you we understand, both has lot to do with the sequence. Okay, I mean, if you want to capture something useful out of an utterance, and if you want to do speaker recognition, I mean, make sure what is the, like, it's important to see what comes in the sequence. We cannot pick individual units and understand it. Okay, when a speaker, if a speaker speaks something, if just one word, okay, and the same speaker speaks, suppose at other time speaks two three words at one go, so the information in that two three words utterance would be much more in the sequence of information, how it switches from one word to another, how his like tongue movements, his, like, mouth movements, lip movements, so, like, from as he goes from one word to another, as he goes and uttering one word to another, his articulative systems would make very distinct changes, and that might differ from speaker to speaker. So that is important for us to capture. That's why it's very important to capture sequential data, sequential information, and TDNN has been able to do that. You see, like, here they have, on the right side you have this table. Okay, so at the same time, like, I mean, when we do image processing, you see, like, we have convolution filter which goes across the image. Okay, but here, like, you have this like, certain number of frames at one thing. So this also happens in a similar way, just like we do with convolution filters and like, for an image. Okay, here we do 1D, like 1D convolution. Okay, and here the special thing here in this X vector system is that it is time delayed. Okay, we use dilated convolution. Okay, so you can see from the table out here, like, uh, in this column called layer context. Okay, the first column, like, is under square brackets, indicating that it's a range of frames. So t minus 2 to t plus 2 is a range of frames. Okay, but as you go, if you on like, if you look at the next rows, you see these curly brackets. So it is not about range, it is just two distinct frame they are taking. Okay, so this is like, this is time convolution. When we work on image, like, we have certain timestamp. We have the size of a filter, and it goes across the image up, once horizontally, once vertically, and it covers everything. Okay, there's no dilation. Okay, so but dilated convolutions means, like, you can skip some steps. As you can see in the second row, they're skipping some frames. Okay, so that helps, like, reduce the number of parameters. Okay, and so that is one thing. The other thing is, like, the same size of the network will be able to take care of greater context, and what we are looking for right now is a context. That means equation information, great, like, we want the information over, like, larger span of utterance. Okay, so that's why this particular system, which is time delay neural network, has become very popular. Okay, and it is still one of the de facto system. So, like, it takes it captures the sequential information in a much more efficient way. Okay, so this is de facto, I mean, both for your I mean, language as well as, like, speaker recognition. Okay, syncnet is another thing that, the next obvious thing, like, one is the sequential information that is important for such application. The other thing is, like, we have been encoding our features. We have been using like, uh, MSCCs, PLP, those are all hand-coded features, thoroughly, like, researched and experimented, no doubt about it. But then came the idea that we can actually make neural network learn those filters itself. Let us not do the featureization ourselves. So we use parametric kind of filters. You see, like, convolution filters, we understand. Okay, so those weights are, as we go on training the model, the weights are changed. Okay, and so the filter, like, filter, like, the way the filter will work, to the kind of information the filter will capture, gets tuned to the requirement based on how we train it, the loss function that we use. Okay, but here what we like, it has to be parametric. Okay, parametric in the sense, like, you can think in terms, like, just like in case of GMM. In GMM, we know there's a bell shape. Okay, so if you want to train a GMM, what you do, you don't, the bell shape is always intact. We will only train, we'll only look at if it is like more than, and it is n dimensional, so we'll look at the n dimensional mean and n dimensional variance. Okay, if you want training a GMM, so that means we have to fix the different, I mean, there will be n mixtures, suppose. So we have to fix n number of means and n number of variances. This is what we are trying to fix and find out. Okay. Similarly, this will that is parametric. It has got, we only can change the parameter, but we cannot overall change the size of it. So similarly, SyncNet filters is similar. These are like sync filters. Okay. We know this popular like sync signal. Okay. So they look similar. So we will only change the filters, the parameters that define those filters, and accordingly, this whole training process will have help change the parameters, and we don't have to really encode things. Okay. It will decide itself like which frequencies it is important for the task that we are doing. Okay. Whether when we train it for like language, or when we train it for speaker recognition, so it will decide by itself like which particular frequency bands it has to capture. Whereas in case of MSCCs, we already predefined it, so here it is learned. So this actually is very important in the sense it's one of the first work like where we directly converting like audio signal into we're giving audio signal as an input, and we're not having this like intermediate step of featureization. Okay. So now then comes the Ikapa TDNN. You see, like TDNN is still the the back end of it, the core of it. Okay. I mean, I don't like getting bogged down by the different like module name, this and that. Like basically, we have to understand like what are the improvements in this Ikapa. So they have this one thing called like squeeze excitation. Okay. Usually, like when we do convolution, and if suppose we are talking about when we talk about image, we have those three if we have a colored image, we have those three maps, right? Feature maps, red, blue, yellow feature maps, and we know we start with three channels. That can actually be considered different channels. But when it comes to speech, uh, it is one dimensional convolution that we are doing. Okay. So sometimes the definition of channel is not very clear. Okay. Because we have a one dimensional signal, right? So thing is that if you have different convolution filter, okay, different convolution filter would lead to different feature maps. Okay. Suppose there are 4 convolution filters, and we do convolution on top of those signal or features, then we get 4 feature maps. So those 4 feature maps can then act as our channels. Okay. So those channel basically like when we were doing convolution, we used to what we used to do is uh, uh, we used to have a convolution which goes across the 3 channels. Okay. Those convolution filter would actually multiply the weights, okay, which are connected across the 3 channels at one go. Okay. But here what they have done, the squeeze excitation they have channel, so they have added this channel adaptation they have added here. So each of the channel, okay, so they have developed a separate network for each of the channel. You see squeeze excitation block. Okay. So here you can see C stands for the number of channel, you see. So they will use a neural network, and there will be weights there. It will be trained, and it will learn how to scale the different channels. You don't have to treat it the same way. This network itself will give you the values based on which you can understand how you should be weighing each of the channel. Okay. So this is one addition they have used. Besides, they have used ResNet layers. Residual network. Okay. Residual network. ResNet has been also a very popular thing. So these two important additions they have added. Besides text pooling and all, it was prevalent even in TDNN. Okay. And they have used some modification to it, and because of this squeeze excitation block, okay, and incorporating ResNet block, they've been able to outdo TDNN, and this has become the state of the art right now. So similarly, recently, you see, these models are getting bigger and bigger. Okay. And whenever we have situations where we want to import things to mobile devices, so it gets difficult because the footprint is very large. Okay. So people are working in that direction, and you see we came out about TitaNet. Okay. TitaNet is we there's one concept which is there's one concept which is separable depth-wise convolution. Okay. So when we do depth-wise convolution, again the same thing is there, uh, when we do convolution, we do it across all the different channels at one go. Okay, but depth-wise convolution does it a bit separately. It does convolution with a single channel at a time. Okay, which is why the number of weights have reduced drastically. Okay, so this is one addition they have added to this Ikapatidian model, and which is why they have been able to reduce the number of parameters. Okay, and because they have been able to reduce the parameters, so it has got easier to actually port this system to devices like mobile devices and IoT devices. Okay, they have laid the path for it actually. So they have come up with various three versions, like Titanet small, Titanet M, Titanet large. So it is almost Titanet medium is almost half the size of Ikapa TDNN, but it gives comparable performances. Okay, so these are only the new addition. The most important addition is of course depth-wise convolution. There are certain they've used average pooling, okay, which gave some incremental accuracy, of course. Okay, so but broadly speaking, just the reduction in the size of the network simply because of using depth-wise convolution. This is the addition to this network. Okay, so RawNet, you see, like it came out of from audio we are getting it in the raw form. We are featurizing it from the raw form. Okay, we're using audio in its raw form, and based on it, like we have all these residual blocks. Okay, multipath residual blocks. Okay, so it's augmented system. So this is another system which is quite popular, and these things are if for experimentation research purpose, it's very easy to actually log into a one GitHub account and get the download the code and run it. Okay, and it's quite the pre-trained model itself are quite accurate. Okay, so this is the deep learning, the most popular deep learning models that we have. Like when we talk about speaker recognition, and language recognition. So if I have to just repeat those things, like we had TDNN, Ikapa TDNN. Okay, and now recent of late, like Titanet has got very popular, and of course RawNet has been had come into play a little earlier. Okay, so you see, like this trend has been continuing, and now I mean. Uh, this people have been saying that data is is no more a luxury now. I mean it's like it's more readily available, so people have resorted to kind of self-supervised learning. So data is available in plenty, but the thing is that we don't have much data which is properly leveled. Okay, which is why we have to resort, because what people have observed, that those deep learning models that we have just seen, they go on performing better and better, when you go on adding more and more data. Okay, one of the reasons I did not quote any of the results and compare the different models, because the accuracies and the performances would differ, based on how much data you could actually collect for training it. Okay, what are the kind of applications you are trying to train? Is it a noisy environment that you are trying to cater to? Is it clean environment data that you want to work on? So based on those, one has to again test each and every of those models and see which works best for that particular purpose. So one thing people realize, we need more and more level data to be able to get better and better performance. Okay, so but that level data is it's not a luxury, but data which is unlevel is no more a luxury, but that level data is much of a luxury these days. So then came into picture this web to big. Initially they most of these models basically were proposed for speech recognition. Okay, a lot of people, a much larger group of people work towards speech recognition. So web to web is one of this. So here what they are doing, since we got a lot of when we talk about text NLP, natural language processing, so some of the BERT models got very popular. Okay, because they were trained in a self-supervised way. Okay, so people tried training for speech in a similar way. Okay, so they came out with such models, self-supervised model, web to web. But in case of when we talk about text, it is very easy to distinguish between different tokens or different words. Okay, either we can tokens is like the smallest unit you want to consider, like for a given application. So when you come to text, you can consider the words as token, or you may also consider subword as token. Okay, and there are other tokenization technique as well. So, but it is more or less clear. Okay, a word we know which we can easily separate words. So similarly, we can easily separate subwords. Okay, but like when it comes to speech, like it goes as a continuous signal. We don't know how to actually separate, because no one is there to level it. Okay, so how do we self-supervise it? When we have a text data, we have spaces between words, but for audio, we don't have such spaces as such, and there's no. So what we can do is what they have decided over, they have made a smart move, and they they use an encoder. Okay, so the encoder will build a feature in a latent space. Okay, and the latent space, they will do some quantization. So quantization, we come from our concept of communication itself. Okay, so given a we will some levels. When we do quantization, like we fix certain levels. Okay, in this case it will be like in thousands of levels. Okay, so the speech signal will be quantized into one of the many levels that we have, and then that would be our because it is continuous, it gets difficult. So what we did, we make it discontinuous, discrete, so to say. With quantization model, we have been able to make it discrete, and that's why training becomes easier. So you see, this concept they have used is like masked prediction. They will latent feature encoder will produce embeddings in the latent space, and some of these embeddings will be masked. And we have the context data, which is basically a transformer model, which will try to predict those masked masked features. Okay, which in the context form. So then what happens, like it's like if one has if the network is finally able to do it, that means the network has learned the context, how to find the context. Okay, suppose you are marking like first few words. Okay, and from the last four words, it is able to predict the first three words. That means the transformer has learned how to understand the context. Okay, so that is the whole job of this training. So understanding the context means understanding the meaning of the meaning, and how relevant it is. So that is all the information that we need, right? So this is how we are training, like web to web training. If you go into details, there are things like contrastive learning. To they use some negative samples, so that the network also learns how to how to disregard or like normalize out those negative samples in case they get it. Okay, and then they have the positive samples, so that they learn like how to get the right contextual information into the embeddings. Okay, so this is web to web. Okay, so next comes the WebLM part. It is just like almost the same as web to web. They have the same kind of philosophy of training. Just if you added few things which made it a little more efficient. Okay, web to web had this position embedding, which was more or less like fixed. Okay, but they have a relative position biases. So the more information like among the quantization units can be learned in you can encode more information into the model if you use relative position in case of just fixed ones. And then they have done something like utterance mixing. Okay, they've cut pasted utterances, okay, accordingly. So that made it more robust. Okay, so this WLM is from Microsoft. The other, I guess, is from Facebook. So they've also used a large scale of data, and they've observed certain improvement in year. Okay, yeah, if you see the performances, I've basically noted down the speaker variation part of thing. You see, like here they have mentioned all the deep learning models as well as the pre-trained model that we were talking about. You can see like but ENN is not it's still like one of the state of the art model. Okay, I've taken this snapshot from this particular Microsoft link. Okay, so voxel, they are divided into three categories. This H actually represents the hard category. Okay, that's why you see the ER is a bit on a higher side. Okay, so as you can see, those big WebLM models are giving lesser ER. That means it is performing much better. Okay, the large video. This is like once we use the pre-trained model, which is available. Okay, but if we want to do it some fine tuning, if we have certain, if we are working for a certain application, and so specific to a domain, we would like to collect those data, and then we do some fine tuning. Okay, and after that fine tuning helps improve the accuracy. As you can see, like there's a difference like in ER. There's improvement like in performance, like as we go about fine tuning each of these models, be it WebLM or be it web to web vector. Okay, so this is how, like, today this job of speaker verification and language identification has boiled down to using like large language models, like these large pretense self-supervised models. Okay, we also call them universal models. Okay, and the trend nowadays is like just fine tuning this for any of the downstream tasks that we want. Okay, so for that, like, the most important aspect is like the collecting the kind of data. Like, if you want to these models are readily available, but if you put to any situation, it might not work the way you want it. So the challenge nowadays is like, you given a task, given a problem, we have to identify what is the environment there, what which data actually truly represent that situation. So we have to collect that kind of data. Okay, and figure out, like, how we can obtain that data from other sources, or if required, like, we'll have to generate it. Okay, and then, like, we'll have to fine tune, like, any of these models, okay, with that data, and to get the kind of accuracy that we desire, and which can actually be production ready. Okay, these models are very good, but like, as such, these are not production ready, because I mean, a lot changes, like, when you change the domain, because there will be a lot of data mismatch. Like, if you think about specific, when we think about specific applications, yeah. So you see, like, so some real world applications that we have for speaker verification, or be it language recognition, like all these
Hello, Dr. Azhar. Hello. Gaurav, can you hear him?
Yes, sir. We can't hear the speaker.
Yeah, I'm sorry. There could be some network lag on my side. Sorry about it. Yeah, I'm audible, I suppose.
Yes, yes, please continue.
Tell me, my slide is visible. Just few slides.
Yes, it is visible.
Okay,
Layer
okay.
one application.
Yeah. So I hope I was here when I got disconnected. So we have these applications here. So our like call center agents and all, they've got replaced now. Like no, I mean, we are assisting people. It's not like we have completely replaced it, but the work has reduced, and then manpower also has got reduced. Okay, I mean, the requirement for manpower has reduced drastically, because most of the things, like, we are able to detect the language, we are able to, like, like, pipe it to a certain ASR and do the understanding with our NLU technique, and we were able to understand the speaker identity from the voice, and like we get the credentials ready before the before the executive, so they can make informed decision based on that. So these applications are very much, like, in implemented these days. These applications are very much like, they do exist in the market, and they have a good market, good business prospect. Like, I mean, that it drastically reduces the manpower requirement, and like makes life much easier. I mean, you can do the same stuff at a much lesser cost. So we do, like, forensic application, of course, like, it's one of those applications, and we personally don't deal with that. Like, banking and financial services, okay. The transcription and translation, like, there are, like, when we deal with, we have some foreign clients, like, so we are able to, like, translate their languages into ours, and accordingly, like, do the business logic required for the different services. So they could be conversing in their own language, and we accordingly, like, do it for our the same business logic can be performed. We don't have to build a separate business logic for them. We just have to translate their language into ours. Okay, the banking voice assistant, which is it's in the market, like, for a long time right now. So these things, like, are existing, and but things that they require more and more, like, kind of refinement, and especially in Indian context, since we have different languages and we have a large population. So yeah, we have a very large population, so I mean, we have numerous problems. Okay, so there's still a lot to do, like, in terms of achieving better accuracy in, like, unfavorable conditions. Okay, when we have a very clean data set, each of the model is doing really well, but in case of unfavorable conditions, we have a lot of research to do, and like and a lot of performance, like, improvement which is required. Okay. So these are challenges, like, I mean, so I mean, we have big models giving very good results, like almost more than 99%, but thing is that, like, when it comes to our application in our domain, so then the problem starts, like, we cannot really port those model and use it for the same purpose. There we face this data limitation. We don't have ready-made data available with us, like, so like, we're not getting real-time performance. Like, we cannot be expecting like big GPUs in every system that we build. Definitely, when we work, we think about certain applications, and that applications has to be cost effective. So we can't be thinking about very high computing resources, which is why this real-time performance becomes an issue. So we have to decide which particular model that we have got to choose. Okay, so and similarly, like, this robustness and adaptability to unfavorable conditions. Okay, it has to have low footprint. Okay, that means the size of the model shouldn't be very big. We cannot port it to many of the devices. Okay, and like, these are the things, limitations that we face when we try to do speaker recognition or language recognition in our own applications. Okay, and one big thing, like, nowadays, that we have to look for more and more applications that we can build. And this is one future scope of work. We have the models ready with us, like, we can conceptualize more and more applications, and they can make then we can make use of our expertise and build, like, cool application that can be marketable, and like, it will make life easy for people. Okay, so this is what I just wanted to this is the perspective that I wanted to share with you today. I mean, that's the end of my talk here, I think. Thank you.